eLearning Academy. Today's webinar topic is From Control to Value AI/ML in Refining and Chemicals. We have an overwhelming response from many countries, and we welcome you all. And hope you all will have a very informational and interactive session today. Before we start, let me discuss a few house rules. The webinar will be 40 to 45 minutes long with a 10-minute Q and a session. You can enter your question in the chat box during the presentation, which will be answered at the end. The webinar will be recorded and available on the OMS eLearning Academy website. There will be a 2-question poll at the end for your input. Please give us your candid feedback at the end via the redirected Google form. This webinar will teach you 3 concepts related to the From Control to Value AI/ML in Refining and Chemicals. First, leverage ML to streamline operations by continuously analyzing data and adjusting real-time processes. This leverage minimizes energy use, reduces raw material waste, and maximizes output without compromising quality. Secondly, utilize machine learning models to detect patterns in equipment behavior, enabling early warnings of failures. This allows for predictive maintenance, extending asset life, reducing unscheduled downtime, and improving plant safety and performance. Last, ML tools provide actionable insights from complex datasets, enabling stakeholders to make quicker, evidence-based decisions. This enhances agility, minimizes human error, and improves strategic outcomes across operations. Today's webinar is hosted by OMS eLearning Academy and presented by distinguished speakers from our collaborator, oPro.ai, a pioneer in AI and ML technology for the process industries. I welcome our esteemed speakers from oPro and the webinar host, Dr. Suresh Agrawal. About the host's organization, Offsite Management Systems, LLC, was founded in 1998 in Houston, Texas. It's chartered to provide consulting and refinery automation project executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. Rob Christensen is a seasoned leader with 25+ years in B2B tech. Rob has led successful exits and IPOs, bringing deep expertise in SaaS and enterprise software. He holds a BS in chemical engineering from Texas A&M. Dr. Tim Spinner is an expert in advanced control and real-time optimization. With a PhD from Texas Tech, he develops innovative solutions that drive operational efficiency for clients. Dr. Roberto Linares has 20+ years of experience in industrial software and AI. He specializes in data reconciliation and optimization, holds a Ph.D. from Texas A&M, and delivers practical AI-driven solutions. oPro. AI delivers AI-powered deep learning optimization for intelligent process automation, helping organizations design, build, automate, and manufacture more efficiently and sustainably. oPro. His world-class machine learning experts and engineers ensure customer success by leveraging proven AI solutions and deep subject matter expertise for real-world impact. Thank you all for attending this informative webinar. To appreciate your efforts, we have 2 complimentary gifts for you. Please stay until the end to learn about them. With this, let me request that oPro's CEO, Rob Christensen, start the webinar, followed by Dr. Tim Spinner and Dr. Roberto Linares to conclude it. I will be back at the end of the presentation.
Thank you, Daisy, for that introduction, oPro.ai. So oPro is actually a spinoff from a company, Petroleum, whose CEO and founder, Eric Zing, if you believe Computer Science Magazine, is the greatest #1 AI researcher in the entire world. He actually runs the department out of Carnegie Mellon. And when I met Eric, his goal was to create a basically one framework, one platform to solve any problem in any industry through engineered AI. And my experience in the automation and petrochemical and chemical space, I thought that we could use this platform to, solve some of the problems that we've been facing in process control for years. And so in 2021, we spun off from Petrum and developed and created oPro.ai for really just to focus on the oil and gas, petrochemical and chemicals markets with this technology. So we inherited about $30 million of R&D. Important because that gives us a framework and a foundation to be able to really implement these types of solutions in the APC and RTO environments very quickly. And because Eric's background was around parallel processing large data sets, our technology is unique in the fact that it can handle these very large data sets in the process control world and give real-time optimizations across, again, these very, very complicated multilinear problems. Our software, our team brings a real expertise into how we implement these solutions, because these are very practical solutions with physical boundaries around the process and around the facilities. And we have a very much an open box and collaborative approach that we use with our customers because hey, as we are experts in AI and machine learning, our customers are experts in the way that they look at their processes and understand their processes. So we have a very much a collaborative approach implementing these solutions across our customers' applications. We've been around for 3 years. And we've done a lot of very, very good work in the refining space, doing a lot of work in fractionation, naphtha hydrotreating, desulfurization. We've also done some work in the chemical space around cyanide and those types of things, in multiple industries, also in the steel space and cement space. And it's because we have an incredibly deep team around the expertise needed to implement these solutions, including, world-class engineers who'll be listening to Dr. Spinner and Dr. Linares here around the practical applications of that. But really, it gives us a foundation and a platform to really solve these problems with this expertise for our customers moving forward. So with that, I'll turn it over to Tim and let him talk a little bit about some of the details and some of the successes that we've had.
Thanks, Rob. Okay, as Rob mentioned, one of the core things we inherited and built on was this deep learning platform. We've configured this for advanced process control and optimization applications. But in the future, this is a flexible platform able to handle all sorts of large data sets. So in our case, we're using control system data, or PI data and lab data, and we're using it to create and then run online inferentials, dynamic models for control and optimization functions. So this platform. So with cybersecurity, we've successfully deployed this in the OT environment, in the control system environment, but it's also available for other applications. If it suits your needs, we can deploy this in the cloud, in your cloud, whatever vendor you wish us to. So it's a very flexible platform and efficiently solves these deep learning optimization problems. All right, so I'll just go through this small use case we've prepared just so I can show you some example models from our platform. Let's see. So this is a very nonlinear reactor from the literature, and it has a variety of competing objectives: maximize throughput, maximize the selectivity for the wanted product, and then it has typical control constraints And for this case, we select two manipulated variables, so to two variables that the optimizer can move, and you know, several constraints, several competing objectives, and several disturbances. All right. Okay, I just wanted to demonstrate like other industrial processes. This example process exhibits large variations in your first derivative and your gain that we usually use for control and advanced control applications. So here in this application, we're seeing orders of magnitude shift in gain. If you go over a large region, so we can do this type of analysis with your data, and once we do this type of analysis, we can assess how many, what size of a problem is suitable for deep learning optimization, which part of the problem can we do with traditional modeling technology. So in this case, this would be an example of a constraint or objective variable we want to use the deep learning modeling on. All right, so just a little bit about our modeling technology. So we use these autoencoder networks. So these are well suited for time series data. So you can choose different nodes in these networks like LSTM or GRU. So we take your data, we have our own proprietary version of this sequence to sequence models, and we create models of all the inputs to all the outputs, and review them internally, and then review them with your team. Okay, and so here's coming up to the type of results we would review. All right, so this is an example of different outputs and showing the model fit. So these are there's two lines on each plot. We're getting a very good model fit from this. This is simulated data. It's not amazing that we could overfit to this data. However, in the following slides, I'll show you it's not really overfit. We're getting some consistent dynamic model of these different outputs. All right. So this is a example between a feed temperature and reactor outlet temperature. So as the process conditions change, we could get different dynamic curves. So you don't just see gain shifts. We actually capture the shifts in dynamics with our technology. So at the end of 60 minutes here, we see the final gain. So you see a variation there, but you can see some curves shoot up much faster than the others. So actually there's differences in dynamics that are important for control. Okay, so we do this set of, we typically plot dozens of these dynamic curves together to look at this variation. We can plot the gains over time and different XY plots of the gains versus inputs and outputs, to kind of explain the nonlinear effects we see. But we always do this type of histogram. We look for the entire range of the gains and make sure it makes physical sense. We make sure we don't cross zero. The gain doesn't flip sign unless it's expected in that case, unless it's wanted. And then if we see behavior we don't want, like a gain headed towards zero, which would lead to large control moves, we can tune the training process to eliminate those gains. So that's one advantage of this whole process is that, yes, it's a nonlinear model. Yes, there can be large variations in the model behavior, but we'll examine it all. And then if there's unwanted behavior, we can go back and tune that out during the training process. Our models tend to, we can fit on the the most trusted data, and then if you want to test against a wider variety of data or train against a wider variety of data, we can follow up with that and keep the majority of the effect with the most trusted data, and techniques like that. So here, yeah, we captured that original order of magnitude shift in the gain for this variable. So overall, this deep learning optimization can capture the underlying nonlinearities in the data. Yeah. So after the modeling process, now it's time to think about control and optimization. Okay. So here, with the main objective function is, okay, produce more product B. So we have which is a function of the feed and the conversion. So we look at the output analyzer on product B. We have the two MVs, two decision variables, feed and coolant flows. All right. And then over on the right-hand side shows how for one set of disturbance conditions over a variety of different different decision variable values, the objective function shows this a nonlinear peak, an internal peak. I looked at seeing if we could use some kind of composition constraint or something like that to capture this peak to try to, linearize this problem. In this case, it's not amenable to that. So we need a technology that can do this internal peak finding and utilize the deep learning models. All right. So we use our our proprietary solver for this. All right. So we have a solver that can solve both steady state and dynamic, give a steady state economic optimum, and also provide a dynamic trajectory for control, for reducing constraint limit violations. All right, that's the base of it is a genetic algorithm. We've also, and that allows us to find, if there's multiple peaks or even if we're doing that nonlinear search for the peak, that allows us to find the global optimum under any condition. Okay. We also have gradient methods to follow up on, and we especially use those during the dynamic control calculation. Okay, in the bottom left here, I say we have two modes, RTO mode and APC mode. So you can run this as just an optimizer that writes targets down to an existing APC. So compared to an existing APC, this would include, it might include constraints for multiple units. This application would contain all of your nonlinearities, and then it could write down targets or limits for your lower level APC controllers to achieve. So if you have APC in place, this can sit on top and consider multiple objectives and nonlinear objectives, and do an economic optimization, and it could sit on top of multiple APCs also. generate targets to each of them. Okay, and then we also have APC mode. So if you don't have an existing APC on an application, we can do both that economic optimization, nonlinear optimization, and also do the dynamic control, like an APC would, all in one application, all configured in the same place using the same models. And you're able to, update your objective function online. So that's one of the points over on the bottom right. We get asked a lot, since another AI technology is reinforcement learning. How do we compare to that? So we don't do any training on our optimization. So the training's only on the model side. So the optimization's all done online. That's is using the efficiency of our platform to use whatever hardware you bring to the table, CPU or GPU. We compute this optimization online every minute or 2 minutes or 5 minutes, depending on your application. So you can update your objective function online, update your economics online, stream your economics from Pi or a different system, and this will update in the next solution cycle, so in the next minute or 5 minutes. Okay. So you do all these updates online, objective function parameter updates, limit updates. There's no retraining necessary. Okay. The case where you would need retraining, of course, is if your operation shifts in a way that the models don't generalize to. So we have a piece about monitoring that online, but also we can handle this online also. So we of course have measurement bias updates to our predictions. We have something called a gain factor, which sort of lets you adjust the response size of the models. And then we have different abilities to temporarily overwrite models online. So you can keep your application online while we do any retraining necessary. So a lot of our customers want to get this in their own hands. So we have our well tested, something we've used internally, a notebook based interface to run the model training, inferential training and model training. And actually we've had customers use this and deploy models online, so that they've actually done their own deep learning models. But it's not the usual interface that engineers are used to, in our industry customers in refining and chemicals. So then we're gonna have a web browser based tool, so that you can configure your model training, configure the tags, configure the training ranges. You might want feedback from us on some of the deep learning model parameters to use, and then normal model information, sample rate and such. So all this can be configured in the web interface. And then we're also developing this data selection tool, and it'll show you the different ranges used for training, validation, test, things you marked, globally invalid, due to the unit being down, things that are invalid for a certain tag or a certain submodel. So all that also available in that web interface. So, our aim is to get these tools into our customers' hands, and if they want us to do the modeling, we we add the resources. If they would like to, or find a third party to, we have the platform available for them. And then, yeah, so, it's we're meant to be a, software vendor someday, but in the meantime, we'll guide you through this process, or for people that for companies that don't want to take on the responsibility of model training and maintenance, we can do that for you. I think it's time to hand over to Roberto.
Yes, Tim, thank you so much for introducing the methodology and our technology. I would like to start by giving some of the customer feedback that we have been receiving. By doing these projects and implementing these applications, the deep learning technology, of course, is trained with more data. We are looking at more, a larger regimes of data. So we can expect, as we have seen, and they have confirmed it, that the application can run efficiently under different regimes. Sometimes if you have an application that is linear and you are below a certain capacity, probably it's not going to perform as well because the delays have changed, some behaviors have changed. So you will expect that. Also, there is no linearization of the objective function. So the objective function can be of any number of terms. And this is particularly important when you are doing real-time optimization or planned optimization, since your optimization function can vary, and you can pass variables and parameters, and then you can update the parameters as needed. For example, cost values, price values, etc. And you can also change the objective function on the fly, meaning that, let's say, certain variable is not important for this time, or let's say for a certain season, right? Let's say you don't care about vapor pressure, in the winter. Let's say that you can zero that out, and then the optimization is just going to consider the other variables as well. We can develop these applications for large problems. The way that we approach the problem is kind of like divide and conquer, I will say. You can create models, submodels, and assemble those in a way that you can predict the whole thing and then optimize for the whole data set. And as also something that our customers are saying is that for them it's strategic that we have a platform, not only because we can do it MLOps and we can control multiple things and monitor. Is because the customer has resources sometimes to do their own applications, and we are doing that as well, having a platform that the customer can use. So after the completion of successful projects in other industries, like ball mills, calciners, clinker coolers, etc., we came into the oil and gas, and the first use case that we did was a fractionation system. So here we just see the depiction of one of the distillation columns, in which, of course, you want to maximize the feed rate to process more feed and get more revenue. You want to look at the constraints, the products and bottoms, pressures inside of the system, accumulator levels, and all of those things. And you want to, of course, prescribe optimally to get more product. You want to operate at the optimal reflux flow rates, and any heating, any heating that is used to minimize that. So that specific fractionation system that we did is composed of 4 columns: the ethanizer, the propanizer, the butanizer, and the isobutanizer. So as you can think about the use case, is really a large problem that we want to control and optimize. Here we are looking at the typical spread that you have between the products values, and that is around $1.38 per million of SCOF. For the we compare the initial capacity that the current MPC had at the plant, and then by comparing it to the 4% increase, we are able to see margin increase. And this is not only revenue, this is just real margin, right? Given to the customer by the application. This is just by maximizing the feed rate to the units. Other values, of course, exists because you can reduce the product giveaway and you can reduce the energy intensity. But those were not added in the analysis, but as you can imagine, they will just only add to the value. So that's for the APC type of application. In the next slide, if we go to the next slide, we can take a look at the other use case. Here we're looking at the plan optimization. Other cases, other people call it RTO. Here, this is more about the coordination of existing units already having some APC. It could be from different vendors. This RTO is looking at the overall optimization. What is the best way to produce certain amount of product? Some of units are more efficient than others, probably because they have. In our case, we have seen that the customer is trying to coordinate 3 units. Some of them they will process the low molecular weight, heavy products with different, let's say, octane destruction. So there is always an optimum, right? And for a human, it's very, very difficult to have in mind the economics and also control, in a stable form. So this type of applications sit on top of the APCs. Of course, we look at the overall economic function and the main pace setters for every unit. And if we take a look at the next slide, we can take a look at the way that these naphtha hydrotreaters are being optimized all together by, and here we are just comparing from an independent non-optimal strategy of control, which of course works, but then in a coordinated fashion, we can get more revenue by doing fine adjustments to the manipulated variables, so we can get an increase in revenue, maximizing the margin, optimizing the products as well. Could we go to next? And this is the platform running on-prem, right? So we have our inferencer and optimizer on-prem there, talking via MQTT to the edge data collector and OPC to the DCS. So that is everything running on-prem. We train the model we train the model on the web, and then we can read data so that we can monitor the model. But we can run both on-prem, completely on-prem, or we can be a hybrid, right? So something that is very important is that we also have MLOps, and that's good for the model development, right? To be fast, right? To also we can think of this as in software development, that you want to know what version you are, and you want to track the model. Let's say you have a good model, you want to be able to reproduce it, or if you want to go back because let's say a particular model was behaving better before, we can roll back, right? So we can support retraining of specific submodels, right? And then we can always look at the performance of these models in real time. right? So that's something very important. It's not just about the algorithm. It's be able to reproduce the the performance and the behavior, right? So you don't want surprises in operations. And of course, we need model updates. And the reason that we need model updates is because there is a process fouling in heat exchangers, and there is aberration and new conditions that for which the model was not trained for. So there is decay in catalyst. As you can expect, probably the yield goes down because your catalyst is being poisoned or is being degraded. Also, your analyzer accuracy can change. So all of those things are basically things that need to be considered, and we should be able to give the customer an updated model in a fast, so that they can prepare and update their system. So, as Tim mentioned this before, that there is no perfect model and no perfect. The model, of course, at the beginning is going to perform very well, but let's say that we talk about this degradation, things that happen. We can always adjust the gain that we see, right? So we also have a bias filter, and then we have different ways of overriding the behavior of a particular model. So we can have a linear model specifically for a certain variable that we want to say wait for more data. So we can always for let's say 95% of the model is deep learning and 5% is it just has linear dynamics. It's possible to do this mix and match. And that's it. This is takes us to the end of of our presentation, and we will be glad to answer any questions.
Thank you for sharing this incredible knowledge with OMS eLearning Academy learners, and looks forward to many such webinars in the future. The webinar slides 10 through 33 are copyrighted by our collaborator oPro.ai. We will now begin the question and answer session. You can email us any more questions at the email address below and the ones you posted in the conversation.
Dr. Suresh, we appreciate everybody joining. And if there are questions that you have,
would you kindly take a moment to respond to 2 multiple choice questions? First, what specific operational challenges in your refinery could benefit most from ML solutions? Second, how can we integrate ML initiatives without disrupting existing workflows and business priorities? Thanks for participating in the poll. Your answers will give us insight into our webinar content. Our complimentary gift is an ebook with 250 plus pages after you complete the survey. We provide a free 1-hour consultation with our academic director, the webinar host, Dr. Suresh Agrawal. Please take advantage of this chance to talk to him about any problems you are having in your refinery, or how to sign up with our academy to receive the benefits of e-learning. We have now concluded our presentation for Webinar-17. Our academy has offered monthly webinars on fascinating subjects related to downstream refining operations. Our next webinar in the series will be Fuel Blending 4.0, Integrating Digital Twins for Refinery Operations, the 18th webinar in the Master Series, which Dr. Agrawal of OMS will present on June 18, 2025. The webinar will explore how combining AI/ML with digital twins revolutionizes fuel blending, eliminating traditional analyzers, and optimizing real-time processes. The webinar will discuss how digital twins replicate physical systems to ensure quality, cost efficiency, and compliance without expensive analyzers. This webinar will teach you how AI-powered digital twins predict equipment failures and reduce unplanned downtime through real-time monitoring. Lastly, you will understand how this approach reduces emissions, improves resource use, and increases profitability while maintaining high product quality. Remember to set up an account on LinkedIn. We are beginning registration on LinkedIn on June 1st. We hope to see you at the upcoming webinar. When you exit the webinar, It will lead you to the Google survey form, where you may provide us with insightful comments. Thank you, and have an excellent remainder of your day or evening. The webinar recording will be available on our Academy website in a few days for you to review again. Please register for our next webinar, Fuel Blending 4.0, Integrating Digital Twins for Refinery Operations, on June 18, 2025 at 11 MCDT, as it will be posted on LinkedIn in a few days.